colleagues, I'm glad to hear again in our seminars. We will start our afternoon seminars, and let me introduce our today's speakers as Professor Simone Ciani from University of Bologna, Italy, and his talk, I guess it is very amazing talk for us, the anisotropic de Giorgi classes and the regularity of solution to some anisotropic elliptic equation. Prego, professore.
Thank you, Natalia. Thank you. First of all, I would like to say that I would like to thank all the organizers of this seminar, and to say that for me it's an honor to talk in front of you. And so, how Natalia introduced the talk of today, this seminar will be about anisotropic de Giorgi classes, and in particular, we will make a little detour on the classical de Giorgi classes and some proposal about new de Giorgi classes that somehow enhance the complete theory, or a more complete theory about anisotropic elliptic equations. So let's start. Here today we will make a little introduction about the anisotropic problem. So telling the story, the origins, and a little bit about the setting. Then we will introduce the anisotropic, the Giorgi classes from the very beginning, when the isotropic and the classical ones are presented. Then in this context, we will see what happens of wrong. What is the problem? Why can't we describe the same properties of the functions belonging to these energetic classes? And finally, we will see some local regularity result for solutions to elliptic equations and parabolic equations. And in the very end, then we will propose a new approach for the definition of these anisotropic de Giorgi classes based on the regularity results that are available. So we go on, and here it starts the introduction of this kind of anisotropic equations. We consider a class of differential equations of the kind AU minus divergence of a character field, which has a particular behavior. From above, it behaves like, let's say, the component of the gradient I to the power pi, and from so this is from below, and from above, it's bounded by this component of the gradient to the power pi minus 1. So in this particular framework here, the divergence operator A, it's similar to the one of the P Laplacian when all pi's are equal one to the other, and in the case of Laplacian when all the pi's are 2. But already from the very beginning, the equation is not the same, because it weights not all the gradient, but each directional derivative is on a particular weight. So about this partial differential operator AU, we can just describe it more simply. Have a look to the prototype equation, which is the following one: minus anisotropic P Laplacian of U is equal of this formula here. As you can see here, which is better explained than in the properties of the field A. The equation is similar to the P Laplacian, but not so much, in the sense of the fact that it degenerates along some of the coordinates. For instance, we could have a solution of the P Laplacian in one variable and a constant in another one, so that in some variable it can become degenerate or singular if we allow pi to be whatever from 1 to infinity. Also, in the following, we will say we will always suppose that the pi's exponents, they are ordered from 1 to infinity, with no restriction in this very definition of the operator AU. Well, this prototype equation of the anisotropic P Laplacian is actually a minimizer, a minimum of an energetic functional, which is the following one, Fu. Okay, go on, of this functional FU is an energetic functional that it is in itself an anisotropic one. We consider it on a bounded set of Rn. This functional FU is known to be the prototype of a class of particular functionals in the calculus variations, which are called non-standard growth functionals. In particular, these non-standard growth functionals, they are harder somehow to describe, and the properties of the minima, they are not known yet completely. The picture is not complete. How to define this functional? Where does it act? It acts in a space which is called an anisotropic Sobel space, which is the space of functions in W11, such that the partial derivative, ith partial derivative, lives in the LPI. So it has a different integrability. The functions of this space, they have different integrability of the partial derivatives.
Simone, excuse me, I have some question about locality. Why you need here local space?
Why do we need? I mean, here we are just describing the compact sets inside of Miga, but in the general framework we can ask for the whole integrability. So W1P omega, yes.
It means you want to cover all boundary condition, maybe, yeah? For this reason, you take here local.
Yes, exactly. Yes.
Okay, thank you.
You're welcome. Okay, so yes, because in this case here, to answer the question, we are considering local weak solution of the associated Euler-Lagrange equation. So local weak solutions of these equations. We will not introduce the whole definition of a local weak solution, but we will just talk about solutions in this seminar. So, in particular, the investigation of the basic regularity properties of the minima of this Euler-Lagrange function FU, that we will make an investigation of these properties of regularity of the solutions of the Euler-Lagrange equation associated to this functional. We will do it starting from boundedness and looking for the continuity and Harnack inequality. So let's call it zero regularity. All the other theory concerning Lipschitz, C1 alpha regularity, and so on, which is it's a beautiful, incredible theory, will not take place in the following. We will care for the moment only about the Hölder continuity, local Hölder continuity of the functions of the solutions. So our first idea is that with no restriction on the exponents pi, they can be whatever from 1 to plus infinity. There can be also that some minimizers, some minima of this functional FU, they can be unbounded. And here is an example taken from the late 90s 87 from Marcellini. And this example, this counterexample, also another one was provided a little before by Giaquinta. They say in short that if pi's are too far from each other, we can have a minimizer of the an extrema of this functional FU, which is unbounded. And so the question is, if we want to make a theory of regularity complete, a meaningful theory of regularity, we have to avoid these particular solutions that are unbounded, and we don't want them. So this means that a reasonable theory of regularity for these minimizers has to take into account the condition of on the exponents which are here. So minimizer of this functional, they are bounded when the maximum of the pi is smaller than a quantity, which is the following one. The theory about boundedness of minimizers to anisotropic elliptic equations has been starting from Kolodi, Korolev, and then followed after 20 years in Italy with Marcellini and many others. And many others also, they studied the boundedness of the minimizers of these functionals in the case of the functionals being defined through convex integrand functions, and so when the minimizers belong to particular Aldrich spaces. Okay, so as I promised before, the problem about regularity of the minimizers of functional FU, it's still open, in the sense that when the coefficients are rough, so when we are considering the whole operator AU, a solution to the equation AU equal to 0 has not been proven yet to be Hölder continuous or to satisfy any sort of Harnack type inequality. This remains still now, after a lot of years, an open problem. And even if the problem looks so much similar to the P-Laplacian one, it is not in the end, because we will see the homogeneity of the operator plays a very strong regularizing property into the energy estimates of the classical P energy, while now this energy, the energetic inequalities that the solutions they have to satisfy, they are different. They are not homogeneous. So in particular, if you pick a solution to the equation, to the prototype equation, that solution U must satisfy the following energetic inequality, also called Cacciopoli inequality, for every real number k and for a general constant gamma. This inequality is usually when p is equal to p, just 1, and we have not the sum. Here we have a gradient on the left. When this happens, the elements of this energetic inequality, they are called elements of the Giorgi P class.
Simone, excuse me, but in classical Cacciopoli inequality, from left-hand side, domain must be less than from right-hand side.
Can you repeat the consideration?
If you consider classical Cacciopoli inequality, yeah,
yes,
from left-hand side, your domain integration domain must be less than from right-hand side, yeah. But you have the same domain K.
The domain. Okay. Yes.
Yeah,
Yes. Usually,
integration domain.
But the fact is that we are choosing a general test function eta. Do you see eta here? Eta has not been specified. So in this case, yes, you're right. Usually when you see the classical Cacciopoli inequality, you don't have the test function eta here. But we will go on this after. You see here there is a classical one. Eta will be specified to be a cutoff function between a ball of radius r, for example, and a ball of radius 2r, so that we will have a smaller integrand here set and a bigger one here, for sure. Yes. This is an important consideration. That's true, but this is because in this energy inequality, the cutoff function eta has not been specified to be a particular one.
I see. Oh, because it look like it's not classical Cacciopoli. Okay, thank you. Yeah, I understand your logic.
Yes. I mean, probably the classical Cacciopoli everyone is used to is the following one here, where one has the gradient to the power 2 here, for example, the modulus of the gradient power 2 in a small ball B rho, bounded from above from an integral on a bigger ball B r, where r is greater than the previous one.
This inequality look like a classical Cacciopoli.
This comes because of the specification of the particular eta, this particular cutoff function. Yes. Yes, thank you very much. Yes, so that's the motivation. So let's say that this inequality here is a little bit a preliminary one, in the sense that we didn't specify in the very first moment the cutoff function. So it's not a complete Cacciopoli from this point of view. It's just an energy estimate. That's true. Yes. However, going back to our problem, so we see here in this energetic inequality that it is not homogeneous. So we don't have the same P and P or 2 and 2 as you saw in the next slide. This really complicates everything in the end, because the levels that we will take Ki, they will be at powers Pi, that in some moments they will They will be important to be bound by the minimum, sometimes in some other moments from the maximum, and this complicates the whole procedure known for the P-Laplacian. On a similar way, when one considers what is the set of self-similarity of the equation, let me go back a little slide. So if we take the anisotropic P-Laplacian equation, which is this one, and consider a classical self-similar transformation, so one picks u and poses lambda I xi instead of xi, what happens is that if you want to have a same solution of the equation, one can have various kinds of self-similar geometries. The one that preserves the volume, the one for which the volume is fixed and doesn't depend on the parameter m here, for our m greater than 0 real number, is the following one. And so the geometry, the self-similar geometry of the equation, which preserves the volume respectively of the parameter m, is this k rho m here. And you can see from the definition in front of you that when pi is greater than this p bar is a kind of average of the pi's that we described before. P bar is the harmonic average of the pi's. Let's just think about it as an average. So when pi is greater than p bar, here when m goes to 0, the directions xi, they go to 0. While on the other hand, when pi is smaller than p bar, in these directions, these cubes here, they stretch to infinity. So in this sense, we say that in this similar geometry, the equation behaves in some direction as a degenerate one, and in some directions as a singular one. So going back to the Giorgi classes, in the 57, Ennio de Giorgi proved the continuity of solutions for second-order elliptic equations with measurable and bounded coefficients. The year after, also Nash did it for the parabolic equations with two completely different ways of thinking. The proof of Ennio worked also for a class of function which is enhanced in these classes, energetic classes that nowadays bear his name, the Giorgi classes. So they consist of functions of Sobolev space W12 log omega, for which there exists a constant, a unique one, for that for all points of omega. Here we should say points omega and a compact set inside of it. So we pick two ready, rho and r. They're smaller enough such that we can consider a ball inside of omega, for which the integral in the smaller ball has, as we were saying before, the integral in the smaller ball of the energy squared of the gradient of u is smaller than 1 over the constant over the difference of the radii from the big to the small ball to the square. This weighted on an integral which is on the bigger ball of u minus k squared. So we take out the level k to the function squared. This kind of energy, now we can really say that these are Cacciopoli estimates. These Cacciopoli estimates somehow describes a whole class of function for which the proof of the Giorgi of continuity worked fine. And in the same way, some years after, by the work of Giusti, Trudinger, and many others, the world of mathematics was somehow ready to define the P, the Giorgi classes. So when one consider an energy functional which has a P growth homogeneous and a P Laplacian, for example, one has instantly, by testing with u minus k times eta, the following Cacciopoli estimates. We call also these ones Cacciopoli estimates when we have a function in the Sobolev space W1P such that there exists a constant such that for each two balls contained in omega as before, and a level in R, real numbers, one has that the gradient of u minus k to the power p in the whole norm is bounded from above from the levels of the function u minus
Simone,
k.
excuse me. In this case, you need convex omega domain, yeah? But it's not true if your domain some concave. No, do you understand my question? Look at, For
Yes, I see. I understand your question. The fact is that we can choose the two balls inside omega as much as we want. So we just need an omega, which is an open set. So we just need an omega, which is a set which is locally Euclidean, for which if you have a point, and you can find always two balls around that point contained in omega, in that localization or around the point of omega, one can always write these energy estimates.
yeah, but you need convexity, because if your omega is not convex, it's not true. No, for example, you have some cusp at the boundary on your domain. In this case,
Yes.
this inequality does not work.
Yes, we are considering open domains, omega,
No,
open boundary,
Simone, not only open, convex domain.
convex domain.
Yeah, because no, do you understand? If you have cusp at the boundary, yeah, how you cover this?
I mean, these two balls here, centered in a point of omega, the point must be in an interior point of omega. So if omega is open, I pick up x0 in omega, it's not in the cusp for sure.
No.
And as being omega open, I can find two radiuses, two radii, rho and rho, such that the balls are contained in omega without any problem. There's no convexity on that. No convexity, no.
We don't need information on the omega. We need on the local inside.
Exactly. The consideration about the energy inequalities, they are only local ones. So for each two small balls centered in a point of the open set omega, we can always write these energy inequalities here. No need of convexity. No.
Okay, thank you.
You're welcome. Thank you. So going on, okay, so we were talking about the Giorgi classes over the two here as defined anciently, and then over order P. These are the Giorgi classes, which are defined for functionals of P order. So like the P, like whose Euler-Lagrange equation is the P Laplacian. Good. In particular, functions belonging to these spaces, so functional spaces for which locally in omega we can always write these energetic estimates here called Kaciopoli estimates. They have remarkable properties, very strong properties, irrespective of their connection with the equation they belong to. So in this case, in this sense, the theory of the Giorgi detaches the function from the equation. We just need the energy inequality. So in particular, it can be proven that quasi-minima variational integrals of growth P, like the one that I told you before, Fu is the integral in omega of the norm of the gradient of u to the power P, they fall into this kind of energy estimates. And the sole energetic condition before, which is this one, it is enough, in this case, this only energetic condition is enough to prove local boundedness of the functionals, the local boundedness of the minima, local Holder continuity of the minima, and when the minima, they are non-negative, also a Harnack inequality. So the theory about these P Laplacian equations, in particular quasi-minima of functionals of growth P, which is even more, it's reasonably complete and very rich. For these ones, we refer to Ladizhenskaya, Solonikov, Raltseva, and the books of Giusti and Di Benedetto. They came very, very much after. Well, in this context like this, we can call what's said before now the classical theory about the Giorgi classes. What we'd like to do in the presentation of today is to understand what could be the meaning of anisotropic the Giorgi classes. First of all, because the theory of regularity of the solutions of these equations, they are still not completely understood. So a first trial was done by Baroni, Di Castro, and Palatucci to define the Giorgi classes, anisotropic the Giorgi classes, d omega pi. So we change only the fact that we put pi here in the name, but we are referring generally coherently to the structure of the functional, which is anisotropic, Fu, the first one that you saw. As functions in W1P omega, so the anisotropic Sobolev space, which are already bounded, because we saw in the second slide that boundedness is not a property of general minimizers of the functional, such that there exists a constant, such that for each two compact sets, one into the other in omega, we can write the Cacciopoli estimates as before. We call it now Cacciopoli because we specified the function eta. So eta here, it's specified as a cutoff function between the two. It's 1 in the smaller and it's 0 out of the bigger. And so we have this inhomogeneity of the energy classes. Very good.
Simone, one question.
Yes?
L infinity is much more for such type equation, because if P grade 1 is impossible in multidimensional case. For this reason, this restriction L infinity is much more. It's not natural for such type equation. It's very strange.
It's not natural for this equation, you say, but we saw from the beginning here in the pi Laplacian that if you pick a minimizer of this functional, then the minimizer it's not necessarily bounded. So either one needs a restriction between the pi's. So we need, for example, Pn to be smaller than this quantity here. Either one already takes into consideration the functions which are already L infinity. So we could also define anisotropic the Giorgi classes in the way such that all pi is the one, pi's are already ordered and Pn is already smaller than this quantity. At that point, it would be natural, but it's the same. I mean, when you consider a function u which is in L infinity, giving no restriction on the pi's for this class, it's saying something more, indeed. Because we know that if Pn is smaller than that quantity, then u is L infinity log. So in this sense, we are taking a class of function which is even bigger than the one that we would take only assuming Pn here smaller than this quantity. So yes, the answer is, it looks unnatural because L infinity log estimates, they should be in the usual case, in the P Laplacian case, for example, or in the Laplacian also, they should be a consequence of being an element of the Sobolev space and the energetic inequality. But in our case, it's not a consequence already because of the inhomogeneity. So it's already really complicated in this sense. And assuming u in L infinity already gives a class of solutions which is bigger than the one that we would have defined by playing on the pi.
Thank you.
Thank you for your question. So this is the idea that they try to put in Baroni, Di Castro, and Palatucci, defining the Giorgi classes, an isotropic one, by this energetic inequality here. But the problem is that, yes, for these functions in this anisotropic de Giorgi class, we can have local sub-estimates, even if they are already bounded, but we can have the estimates for them locally. We can have a Hölder continuity of the function of these classes, but it's conditioned. It's conditioned. It's a stability result. Condition of the fact that there exists a number that we don't know what number it is, such that if the difference between Pn and P1 is small enough, then the function in this anisotropic, the Giorgi class, is locally Hölder continuous. So it's a Hölder continuity conditioned on the distance from Pn to P1, which is not exactly quantified. It's qualitative. And also for this kind of functions, no Harnack inequality, at least for the moment, only for the functions belonging to this space, is known. So it may be that these classes, anisotropic classes, as rightfully your colleague before was saying, they are not completely natural, they seem not to contain enough information for having the expansion of positivity for a Harnack inequality to hold and a general Hölder continuity. The work that I was talking about for the conditioned Hölder continuity, it's a work of Di Benedetto, Giannazza, and Vespri of the 2016. So this is the problem. Defining the Giorgi classes as isotropic one in this way looks not to be enough. It looks that only the information that we have here in these energetic estimates, an isotropic one, it's not enough for a reasonable theory. So what we do is to make a step back and to check what is known already for special anisotropies. In particular, we consider also parabolic equations into our, let's say, our basket, because a parabolic equation is already, in some sense, anisotropic, in the sense that when you do the energetic estimates, we have a term which goes like 2 and another term that goes like p. For instance, if one looks to the theory of singular degenerate parabolic operators of the kind of P Laplacian, the evolutionary one now, this theory has been considerably developed. And by the method of intrinsic scaling, the famous method of intrinsic scaling, Di Benedetto proved that the solutions, they are continuous and they satisfy in some ranges of P also a Harnack inequality. In particular, when P is greater than 2, for sure here P must be greater than 1 and smaller than infinity. There are two main cases, like usual, when P is smaller than 2 and when P is greater than 2. In the second case, we say that the equation is degenerate because the modulus of ellipticity goes to 0 as soon as the gradient vanishes. And in the first case, we say that the equation is singular because the modulus of ellipticity, it explodes to plus infinity when the gradient goes to 0. In this second quality, in this second interval of P, when the equation is singular, the equation is mainly driven by the elliptic counterpart. So about the degenerate one, Di Benedetto proved in 1991 that Hölder regularity for the whole class of the functions U is true. So a whole class of functions U satisfying equations more general than this one, but with the same growth of P, they are Hölder continuous. And this is enhanced not only for the solutions of the equation, but just by assuming that this function U satisfies a parabolic energy inequality and a logarithmic type inequality. Similarly, in the case P is smaller than 2, here there is a little printing mistake, a typo, P is smaller than 2, it's possible to show Hölder regularity and the Harnack inequality by still again parabolic energy inequalities and another kind of logarithmic inequalities. So we take this example as an idea on how to treat anisotropy of an equation. The common underlying idea of Di Benedetto is to use a particular geometry which is scaled on the solution itself to accommodate this degeneracy of the equation. Well, we started from this point of view here to treat in a recent work with Igor Shripnik and Vincenzo Vespri, a special class of anisotropic operators, which are described by the following one. We call them ASU, and they are the sum from 1 to a number S, which can be from 1 to n, of the double derivative. So derivative of is just like a Laplacian in the first S variables, plus the divergence form operator applied to the other n minus S variables in the whole measurable and bounded coefficient case. And we consider this equation for exponents which are from 1 and 2. This equation with a particular structure condition of the operator AI, for each I, it behaves like a P Laplacian, just P. And a particular range of exponents, which is the following one. The remark that we want to do here is that this equation is a special case of the general isotropic equation you saw in the first slide, because we are taking here in the first S variables pi equal to 2, and the last n minus S variables here pi equal to p, singular. So what we prove here in this for the solution, local weak solutions of this equation, it's a regularity result. To do this regularity result, we had to undergo the similar technique of Di Benedetto, we had to apply an intrinsic scaling to the equation. So how to do? In this case, we have just 1 and 2 ranges of pi, all equal to 2 and all equal to p. So we set up this intrinsic geometry, which is the following one. Picked a point in omega open in Rn. We denoted the first s components as x prime and the last n minus s components as x second. And in this case, we considered domains which were the Euclidean product of both of s variables and n minus s variables, where the first ball was intrinsically scaled by the solution itself. So it depended by a radii theta, which is defined by the radii of the other ball rho, but also with a factor m that will depend on the solution itself. With this geometry, we were able to establish Hilbert continuity, local Hilbert continuity or local weak solutions, L1 L infinity bounds for the solution, meaning that we bounded the supremum of the L1 norm of U with the infimum of the L1 norm of U, and an intrinsic Harnack inequality. This work was done with Igor Skripnik and Vespri, and followed another one in 2020, it's not written here, of Nayan Liao and the other two authors before. The particular tools for the regularity of this equation were the energetic inequalities, the classical ones that you saw before that we called Cacciopoli, and particular logarithmic type inequalities that came from the theory of P-Laplacian parabolic equation, which was already done by Di Benedetto and Chen in 1992. The results read as follows. First, we had our L1 L infinity estimate, as I told you before. We picked a solution which was non-negative and bounded already of our equation, fixed a point in omega open, and two numbers, theta and rho, such that the intrinsically scaled polydisk or cylinder stayed into omega. For this case here, there exists a constant such that either a non-homogeneous statement happened. This is because the equation was non-homogeneous in the sense that we have also something more than the operator, or the L1 L infinity Harnack inequality happened, in which we bounded the L1 norm of U in this particular geometry, which is intrinsically scaled, by the L1 norm of U in a bigger ball in the second variables, plus a scaling argument. When the number key is greater than 0, and for this we would like to see that key was a number p plus n minus s times p minus 2. This number is that gives a condition on key greater than 0, which is the same as this one. And when you see that when the let's call them non-degenerate variables, they are s, they go, for example, to 1. Then in this case, we recover a range of key of p, which is similar to the parabolic equation. While on the other hand, when s go very much more to n, to the whole dimension, then the equation becomes an equation which is much more similar to a non-degenerate one. So that here, if one puts n minus 1 instead of s, recovers p must be from 1 to 2. Well, going back to the L1 and infinity estimate, they were very useful, and they proved to be useful also to prove to have a Harnack inequality. In particular, which seems still with the approach of these intrinsically scaled cylinders, we can prove the following Harnack inequality. Picking a solution which is non-negative of the equation and a point in omega, such that you can say that the solution is greater than 0, there must be at least 1, otherwise the solution is 0. And taking a radius small enough such that a particular inclusion of this anisotropic anisotropic intrinsically scaled cylinder stays in omega, and this condition somehow is a geometrical one that we can always assume, but we can also try to avoid this by comparison, as we saw on another seminar of Igor. When the condition K greater than 0 holds true, then we have two constants, K and delta, such that either the solution is already small enough compared to the radius, or the Harnack inequality holds true in this particular geometry. The remark that I told you before is still holding. Condition K greater than 0 links the effects of the singular and non-degenerate parts of the operator that you saw before. So when s goes to 0, one recovers the classical parabolic range of P, while when s goes to n, let's say formally, because s must be a number from 1 to n minus 1, condition of positivity on K reads as P from 1 to 2. So when the equation is non-degenerate, you can choose any P between 1 and 2. The proof of Harnack inequality and L1 at infinity bounds holds because of the particular log estimate. This particular log estimate, that it's quite massive in this slide here, says the following. One picks a bounded weak solution of our operator and consider intrinsically scaled polydisk or cylinders inside omega. Then for every level k and every function c1, which is increasing, one has for each time, for each parameter from 0 and theta, which we call it as a time, even if we are in an elliptic setting, because we are using a parabolic technique, we have this estimate. We can bound the integral of the energy of the solution, that we can see in the big parentheses on the right, times f prime for a factor that depends on second variable and the first variable in a sense that is linked to the geometry of the equation. These particular logarithmic estimates, they exist also in the case, not these ones, but similar ones. They exist already for the parabolic P Laplacian equation. And they prove to be very important for both for the Harnack inequality and L1 and infinity estimates. So that this is the motivation why we say between us a function which is already in the anisotropic, the Giorgi classes defined by Di Castro Baroni before in Palatucci, satisfying this estimate for all such f in C1 and levels k, belongs to a special class, which we call the logarithmic de Giorgi class. The strategy to find these logarithmic estimates is to test the equation with a particular test function, which is defined by f of u. Going on, one can ask himself what is done also in the case of an isotropic counterpart of the equation. Well, it comes out that if one treats the equation only, the parabolic equation with the only prototype one, so parabolic equation associated to the anisotropic pi Laplacian in the degenerate case, so well, all the pi's are greater than 2, but are smaller than a particular parabolic quantity, then one recovers a Harnack inequality and therefore also Hölder continuity. This is the statement of the Harnack inequality for the parabolic counterpart of our equation. In particular, if we pick a non-negative solution of the parabolic anisotropic equation and pick a point of the domain where we have that the solution is positive, clearly here the sense of being positive for the evaluation of the function in a point, it's already a difficult task. I mean, when no continuity is known for a solution of this equation, already saying that the solution up in a point is greater than 0, it's a hard point. Semi-continuity does the job, or we can just apply the Lebesgue theorem of points and say that there must be for sure at least one point where we can define this quantity as a limit, integral limit. Well, if the pi satisfy the range of before that you saw, that we call the finite speed condition, then there exist three constants, C1, C2, and C3, such that we have the following parabolic Harnack inequality. Let's focus a little bit on that. So the value of the value of the function in the point is bounded from below, from the infimum of the function evaluated as some time passing, the time being scaled on the function itself, because this factor m now, it's really u in the point over a constant. But in this case, which is very similar to the one which is known for the P Laplacian, the very difference between the two is that this infimum is taken in a cylinder which is anisotropic and intrinsically scaled itself. It's intrinsically scaled by the solution. It's k rho m, as we saw it in the very beginning, the intrinsically scaled anisotropic cylinders. And the same bound, it's also from below with a supremum of u in a time which happens before. So the idea is, okay, now we have that solutions to the parabolic equation, they satisfy a Harnack inequality. What about if I pick a solution of the stationary counterpart? So if I want to understand what is the behavior of regularity and behavior of the anisotropic P Laplacian by considering stationary solutions to that. Well, the theorem gives a corollary which is very simple, and which says that you have a Harnack inequality weighted on a particular anisotropic geometry. Still, here supremum and infimum of the solution must be taken into a set which is anisotropic and which is scaled on the solution u itself, like in the fully parabolic case. But not only.
Simone, excuse me. In previous theorem, you proved finite speed of propagation, or you state finite speed?
The finite speed of propagation here is proved by Mosconi, Gamze, and Vespri. It's already proved.
You used their results, yeah?
Yes, we used the result to build a Barenblatt solution, a fundamental solution, which is not possible to write because I don't know. At the moment, we haven't found a way to write it, but we stated the existence of a Barenblatt fundamental solution by this finite speed condition and the comparison principle. Then after that, comparing the solution of the equation with the Barenblatt fundamental solution, the abstract one, we covered the Harnack inequality. Yes, so the finite speed condition, it's not inferred, it's really true. I mean, it's coming from an established result of Mosconi, Tutskun, and Vespri.
Thank you.
You're welcome. Thank you. So going on here, we have, an elliptic statement coming from the parabolic one. And that says already something, like a Harnack inequality holds true, but in a particular geometry, which is very different from the one that one has in the P Laplacian, the elliptic stationary P Laplacian case. And comparing the parabolic range with the elliptic one sees that from this corollary, we have not so much information. In the sense that we have the parabolic Harnack inequality when Pn, the maximum of the Pi's, is smaller than this quantity here, the finite speed of propagation, which is smaller itself on the range of exponents that guarantee the boundedness of solution to the parabolic equation, which is smaller itself on the maximum range of Pi's for which the boundedness is true for the elliptic equation. Okay, so the idea of the proof, as we were saying before, the idea of the proof for the Harnack inequality for the parabolic equation relies strongly on the equation. So talking about anisotropic de Giorgi classes, at the first point, it doesn't look so good because we want to define a class, an energetic class of functions and not be linked to any equation. So it was relying on the comparison principle, as we were talking before, and with an existence of an abstract self-similar solution. It was positivity, so we had a bound from below of the abstract Barenblatt solution, which is controlled by the self-similar growth of the solution itself. The key ingredients for this proof here they were L infinity bounds of the solution, L1 L infinity bounds of the evolution, and the finite speed of propagation that we were talking before, for compactly supported initial data for sure. Okay, but all these ingredients here, even if they rely strongly on the equation, they are consequences of a strong property, which is the classical energy estimates that we use massively, and the pre-logarithmic energy estimates that we show here in this slide. What do I mean with pre-logarithmic energy estimates? If one picks a C2 function, such that has particular bounds for the derivatives, second derivatives, and also for this quantity relatively to the PIs, then picking a solution to the parabolic equation and testing with a test function which has separated variables, which means that it's a product of ni, xi, all equal to 0 in the boundary on a localization of the domain, then for every time from 0 to t, we have the following estimates. So as I told you before, already when all the PIs are equal, we have some kind of anisotropy that we can balance between parabolic and elliptic equations. Here we have a particular power of f and u consequently, and then we bound the energy weighted with this f2u. These estimates here, they prove to be very, very useful for the for the finite speed of propagation or compact support of the solution. And in particular, in the case when pi are all equal to p and they are greater than 2, the classical proof of Di Benedetto, as I told you before, he proved that if the functions, they are not necessarily solution, but they belong to some energetic classes which are enhanced by Cacciopoli estimates and logarithmic energies, that the logarithmic energy estimates, they are reminiscent of these pre-log estimates here by a specification of the function f, which is the logarithmic of 1 over a quantity involving u and L infinity normal u. Well, arrived to this point, one is tempted to make a proposal about anisotropic de Giorgi classes, which is, let's say, a restriction of the previous one, because we saw that the classes d omega pi, the anisotropic classes inferred by Di Castro, Baroni, and Palatucci, they were not enough, at least for the moment. They didn't contain so much information. Because of the non-homogeneity, they don't contain so much information about the functions. An idea could be to restrict the set of this function to a restricted de Giorgi class that we call Rd omega pi. That says that if you pick that a function u in the anisotropic Sobolev space and already locally bounded, unfortunately, but if this function satisfies for each function f in C1 strictly increasing, and any test function of separate variables, as I told you before, the estimate, which is similar to the pre-log estimate here, so the integral over k of f prime times eta times the derivative of u minus k to the power pi, it's controlled from above by f u minus k plus and then a smaller power of u minus k derivative. In this case, we say that a function u belongs to the restricted de Giorgi class Rd. Okay, so what is my proposal here in this seminar is to state that these are classes of functions which are enhancing all the other properties of the other classes. In particular, they generalize and englobe the result of regularity that we have until now. Let's see why. First motivation is that if a function is in the restricted de Giorgi class, then it's in the de Giorgi class. How to understand this? One uses just a Young inequality so that the assumption on the energy estimate that you have in the previous slide here, one uses on the right a Young inequality on these factors. to arrive to this stationary version of the pre-logarithmic energy estimates. So these are the same as before, but only in the space without the time variable. Then one chooses f properly to be a truncation of the function, depending if you want to truncate from below or above. And by this choice here, this implies the classical Cacciopoli estimates, so that U belongs to the, let's say, anisotropic de Giorgi classes inferred by Di Castro. Well, a second motivation is the following. If a function belongs to the restricted de Giorgi class omega pi, then that function is also an element of the logarithmic de Giorgi class, which were so much useful in the derivation of the regularity properties for the elliptic singular equation. How can we do? Here again, we do a Young inequality, and we specify the test function eta. Let me go back. Eta here is specified in two variables. If you remember here, we have first S variable, pi equal to 2, last n minus s variables, pi equal to p, smaller than 2. So we specify this eta in this way, and we pick the first test function in the following way. So in the end, what happens is that these reduced the Giorgi classes, they are smaller. Here it's all the two inequalities are inverted. I'm sorry. So the reduced the Giorgi classes, they are contained in the logarithmic de Giorgi class. Is reversed, and also the reduced de Giorgi class, they are contained in the Giorgi class. We reduce the class of the energy of the function, so that in this case we can recover all the regularity results until before. For example, in the case that we examined of the local regularity for the elliptic singular equation, the work we did with Igor, in this case, pi is equal to 2 for the first S variable, and pi is equal to p for the last ones. In that case, the assumption U belongs to the restricted de Giorgi class, and so therefore that U belongs to the logarithmic de Giorgi class, implies the local hurdle continuity of the solutions of the equation. The condition, this is only for the case of the elliptic singular equation. Again, if a function belongs to the restricted de Giorgi class, this class, as you've seen before, it's contained in both the anisotropic de Giorgi class D and LD. So it's a very small, very stringent class of functions that we call restricted de Giorgi class. But still, all the solution of the anisotropic general operator AU equal to 0, all the solutions, they are satisfying these particular energy estimates for C1 functions. So all the solutions of this equation, they are still in the restricted de Giorgi class. So it's natural for the equation in the sense that all the solutions, they belong to this energetic class. And the last remark is that we considered a singular case for pi equal to 2 and then pi equal to p smaller than 2. Also in the case of pi is greater than 2. So let's call it the degenerate one, and the last variable equal to 2, which was a work done by Lishevich and Skripnik in 2009. Also in this case, the regularity of the solution is obtained by a method which is reminiscent of this restricted de Giorgi class. So that's why this class of function is somehow enhancing all the previously ones, and it's fixing that missing information that had the anisotropic de Giorgi class. We pay the price on having a restricted, smaller class of function, but we fix somehow the lack of information given by the inhomogeneity of the Cacciopoli estimates only. So that's the end of the seminar, for which I thank you very much for your attention.
Thank you very much, Simon, for a nice talk. Maybe, dear colleagues, do you have questions, comments? Igor, maybe you have comments?
No, of course I have a comment. Simone, can you go back to the first paper?
First slide.
Yes. First slide, yes. No, I want to say it seems that this equation very simple, but unfortunately it's very difficult. And for example, I want to say that having such results as the Giorgi, the Benedetto, Trudinger, so on. For example, most simplest case, for example, for the pseudo Laplacian, when all pi are equal to p, we don't know the C1 regularity. And for example, we know the W1 infinity result is known for the pseudo P Laplacian is known. It was proved 1 year ago. So that is very difficult problem. More of all, it is not known the explicit type of the fundamental solution for such type equation. Even, for example, when sum of P1, even for the case which was considered in this talk. So I want to say that it seems that it's very simple, but it's very difficult problem. So it's every result in the direction of the which about which say Simone is very interesting. So thank you very much for your interesting talk, Simone.
Igor, you think about singular P Laplacian when P less.
No, it may be singular, maybe degenerate. If all py equal to p, pseudo P Laplacian, there is no result about C1 regularity. There is also result was proved 1 year ago only in the about W1 infinity. Even so, for such very simple, as it seems, equation. So it's very difficult.
Thank you.
Yes.
Yet questions, comments? Maybe some stupid question, but I'm interested in now you say about only local estimate, yes, Simone. But it's possible maybe using your approach to continue your estimate up to boundary. Okay, let's assume the boundary very smooth and consider at least the homogeneous Dirichlet condition. So it's possible, or maybe it's what's difficult with at least the Harnack estimates. Maybe it's possible using your approach.
So about the parabolic problem, I don't know how to do, but about the elliptic problem, we have some ideas, and they go through the definition of auxiliary solutions. So yes, it is possible to study the behavior at the boundary of the points, so attain the boundary continuously, like in a Wiener test condition. But this is first of all, this is not known yet, and yes, the study is possible. It's an open problem, but it's possible. Yes, it's a probable next step, I would say, on the study of this kind of equation. Yeah.
Maybe. Thank you very much.
Yes, but not clear what is difficult, because for classical P Laplacian, regularity up to boundary well known. Yeah, if you consider non-singular case for any anisotropic, maybe is not difficult.
No, it's very difficult problem.
Why?
Because you have the anisotropic problem. For example, if you take one P1 is equal to and other pi equal p.
No, Igor. I want to consider a more simple case. All py grade 2. What do you think about singularity up to boundary? I think it's not problem.
If all PIs are equal to 2,
it is very
No, not equal to. No, all pi grade 2.
No, but if they are not equal each to others, it is very difficult problem, as I said to you before.
Okay.
It's because already the local regularity is a mess. Already the local regularity is a problem. It's not
We
known
don't know
in
the local regularity. Yes, interior regularity is not known.
Okay, thank you.
Yeah, maybe it will your future works. Okay, thank you very much again. I find to some the sign center and reaction, and maybe like here and here. For you have only lines, and I will not have to like here. So thank you very much, Simone, for very nice seminars, very nice talk. So thank you very much, colleagues, for our seminars. And today we will finish. Thanks again.
Thank you very much.
Thank you very much, Simone. Eureka, ciao.
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 Thank you.
Ciao.
Bye.
Bye.
Bye. Bye. Bye.
Bye.